Hello, welcome back. The title of this lesson is called Using Radicals to Solve Equations, and this is part one. I'm excited to teach you this because here you take a step. It's very rare to take a step forward where you really expand your knowledge of what you know and what you can do. This is one of those lessons. If you remember, we already know how to solve equations. We've solved equations where the goal is to get the variable on one side of the equation by itself, and then you then know the value of that equation. So let's just review really quickly the types of equations that we know how to solve. Very simple equations like x plus 2 is equal to 5. You know how to solve this equation because what you do is you do the opposite. You subtract 2 and move it over there, and 5 minus 2 is 3, and so you know that x must then be equal to 3. And you can check your work because 3, you can put it in here, 3 plus 2 is 5. And so there's only one solution to this equation, right? I want you to remember that because there's actually a pattern to it. There's only one solution for the equations we know how to solve already. But in this lesson, we're going to solve equations that actually have two solutions. And as you get higher in math, you're going to learn how to solve equations with 3 solutions, 4 solutions, 5 solutions, because equations can have more than one solution, right? And we're going to talk a lot more about that later, but that is something important for you to know. Everything you've solved up till now, only one solution. Other equations have more than one solution. So let me show you. I'm going to give you some motivation. What we want to do is we want to isolate the variable, but what if that variable has a square on it? In other words, this variable that was wrapped up in this problem, it was x to the first power. In fact, I'm going to put a little first power here to remind you that this is x to the first power. And because it's a first power on x, there's only one solution. That's the pattern. Whatever the power is on the x, on the highest power of x, that's how many solutions you have, right? But let's take a look at another equation down below here, and we're going to solve it in a second. And this equation is x squared is equal to 1. Probably the simplest equation that we can come up with a power on the x that's different than a first power that we had here. Now, if this equation had one solution, how many solutions do you think will be here? There's actually going to be 2 solutions. Now, both solutions to the equation are equally correct. It's not that one is better than the other. There literally just are 2 different values of x that can go into that equation. Now, when you first start learning this stuff, you start thinking, well, why do I care about this? Why? What possible application in the real world could have x squared, a power of 2 like that? Why do I care about solving these? Let me show you one, and we're going to talk a lot more about it in a minute because I like to motivate to you why we're learning this stuff. You may have been exposed just through, popular everyday life about a famous equation, E is equal to mc squared. This is probably, in my opinion, the most famous equation that has a power of 2. And these powers of 2, the square in this case is on the letter C. We'll talk about that in just a minute. But that power of 2 what it means is E is equal to m times c, because c squared is c times c. All right, now in this equation, E is the energy that a piece of matter contains, m is the mass of the matter, and c is the speed of light. So speed of light squared is what is going on there. I'm going to talk a lot more about that in a second because I want to play with that equation a little bit to show you how it's important. Mostly I want to tell you that these equations of solving equations that have squares in them, it's incredibly common because the most famous equation that probably everyone knows actually has a square term in it. But there are plenty of other equations that have squares. The force of gravity between 2 objects like the moon and the earth, or this marker and the center of the earth or the sun, actually has a square term in it. One of the variables in that equation is squared. Also, the attraction of electrons or protons, the repulsion and attractive forces also has square terms. Even the area of a circle, pi times r squared, right? Pi r squared. So there's a square on the radius. Tons of equations in real life have squares on the variables, okay? So this stuff we're learning here is not stuff you throw it away. It's stuff that's critical because there's so many applications of this. So let's put E equals mc squared on the... If you put x is equal to 1 in there, 1 squared means 1 times 1 is 1. So the value x equals 1 is a solution. But there's another solution. Can you guess what it is? If I put negative 1 in here, then negative 1 squared means negative 1 times negative 1. And you know, negative times negative is positive. So -1 times -1 also gives you a 1. So there's, even without doing any work, there are two values of x that work, but they're not any more than two. There are two values, two real numbers that we can put in there and get and satisfy that equation. And notice that the equation has a square on the power of x. So when there's a square on the power of x, there's two solutions. When there's a power of 1 on x, there's only one solution that works. Can you guess what's going to happen when you have a cube on an x? There's going to be 3 solutions. Can you guess what would happen if you had x to the 4th power as the highest power in your equation? You're going to have 4 solutions. Can you guess what's going to happen if you had a crazy equation, which I've never seen in real life, but x to the 16th power? Well, you'd have 16 solutions. All right, so the highest power of x that is in your equation tells you automatically how many solutions you have. And mathematicians have proven that. So you don't have to worry about that. That's already proven for you. In this case, we know there's going to be 2. And this one's so simple, we can guess what they are. But instead of guessing, let's figure out what to do. All right, so let's rewrite this. X squared is equal to 1. Now, I think I mentioned in previous lessons that here we have a square term. How do we undo a square? The opposite of a square, I've mentioned it about 50 times. The opposite of a square is a square root. They are opposites of each other. When you take addition and subtraction, for instance, the addition is opposite or to operation than addition. So addition and subtraction are opposites. Multiplication and divisions are opposites. And squaring and square rooting are also opposites. What that means is they undo each other. If you take addition and subtraction and you say something like, you know, I guess I can go over here. If you say something like, you know, you start with 5, right? And then you add 2 and then subtract 2. Well, I've added and I've subtracted. 2 times 4 is 8. So you see the 8 remains unchanged. Dividing and multiplying are opposites. They undo each other. And addition and subtraction are opposites and they undo each other. And to drive it home, let's take a look at something like 10 squared, which is a square, but then let's go ahead and take the opposite of a square, which is a square root. What are we going to have? It's going to be 10 squared is 100, but we have to take a square root of 100, and a square root of 100 is 10. And you notice that the 10 that was in here, you squared it and then you square rooted it, but you actually got back the exact same thing that you started with. And so the squaring and the square rooting, they kind of cancel each other, and so you can actually draw a little line through the square root and through the square because they annihilate each other, and the 10 just falls. Since I want to get rid of the square here, I'm going to get rid of it by taking a square root. And if I do it to this side, I have to do it to the other side. Now, I'm going to solve this to the end, and then I'm going to show you one additional thing you have to remember to do, but I don't want to get to it yet. I want to solve it here. So let's go through here and say, what happens? The square and the square root, we just showed you an example of where they cancel. So they cancel. The square and the square root is gone. The x, which is what I'm trying to find, is now removed and isolated. And we know what the square root of 1 is. 1 times 1 is 1. So we can put the number 1 here. And the answer is x is equal to 1. And we can check it by putting 1 in here. 1 squared is 1. So we know that this is correct. But a minute ago, we just said there's actually 2 solutions to this. -1 is also a solution. And this is coming about because when we talked about square roots the first time, several lessons ago, I told you that there's really 2 answers to these square roots. There's the principal square root, which is like the positive answer, but these square roots really also have negative answers too, but we don't usually worry too much about it. Now we actually have to start worrying about it because we have to get both answers to the equation. So here's the rule of thumb. When you use a square root or a square root to apply it to both sides in order to solve an equation, when you apply the square root yourself, then in front of the square root on the right-hand side, you have to put plus or minus. And so then the x falls out. The square root of 1 is 1, but this plus minus stays in place. So the answer you really get is x is equal to plus or minus 1. And that's a fancy way of just saying that x can be equal to positive 1 and x can be equal to -1. And these are the 2 answers. And the reason that you have to put the plus minus, it all boils down to what a square root is. Long time ago, we talked about square roots. We said, hey, there's a positive number that falls out of that, but you know, the square root of 4, for instance, is 2, because 2 times 2 is 4. But the square root of 4, you can also think of it as being -2 because -2 times negative 2 also gives you 4. So there's really always two answers to those things. And so when we put a radical in place, a square root, to solve an equation, when we apply the radical ourselves, we have to put plus minus in there to make sure and catch all the solutions, which is going to be 2 solutions. And so we get plus or minus 1, and there it goes. All right, you put 1 in here, 1 times 1 is 1. You put negative 1 in here, negative 1 times negative 1 also gives you positive 1. There's 2 solutions. So from the top, the equations that we have solved before are called linear equations, because when we draw a picture of them, they're gonna draw a line. I'll talk about that later. But there's a power of 1 on the x, and the power on the x tells you how many solutions. There's only one solution here. But the power in this equation on x is 2, and that means we know ahead of time that there's actually 2 solutions to this equation. And so to solve it, since we have a square, we isolate it by drawing a square root on both sides. And when you do that, and they're both on equal footing, all right? Now let's turn our attention and have a little bit of fun, because I don't often get to do this, but it's just irresistible. Let's talk about the most famous equation in all of science, if I can write it correctly, sorry about that. And that's E is equal to mc squared. Now this is not a physics class, but it's so incredibly interesting to me that I have to show you and share with you. Stars everything is what we call matter. It's something hard, right? You can just kind of hit it. You feel it. It's there, right? But Einstein basically said that matter, the stuff that you can hold, can be thought of in terms of energy. It contains energy. And the energy content of this piece of matter is enormous. Any piece of matter that you've ever touched, even something little like this, even something tiny like this little cap, has an enormous amount of energy contained inside of it. And that energy is what constitutes the matter that we can touch. And so that is a equivalence that Einstein proved, and we know it to be true to all of our measurement accuracy because we've built machines that use that principle. For instance, nuclear reactors. To generate electricity, you would not be able to do that if E equals mc squared was not true. So this E is the energy content of any piece of matter that you can think of. This M is just a mass. So the mass in kilograms. And this c is the speed of light. Think about that. Taking the speed of light and multiplying it by itself. The speed of light is so fast that a light wave or a photon can go around the entire planet Earth 7 times in 1 second. Think about the entire circumference of the Earth. Now just do that one time. Now do it 7 times. And here's a second. 1 second, 2 seconds, 3 seconds, like a 1 kilogram potato or something, and you get an enormous amount of energy, an unfathomable amount of energy contained in even tiny little objects. And that's why we can take a very small amount of nuclear fuel, turn a tiny fraction of it into energy, and a nuclear power plant can generate power for an entire city. Because everything that you're surrounded by contains enormous amounts of energy. And the giant ball of hydrogen and helium in the sky that we call the sun generates energy using E equals mc squared. It uses the mass of the hydrogen, and through the gravity squeezing it together, it fuses it to helium and it releases some of that energy that's contained in the matter, and that's all of the light and all of the heat that the whole planet uses, going out every which way from the sun. So I guess I'm trying to tell you, it's a little bit of an aside, but this equation contains a square term on the speed of light. So what would you do if I didn't want to calculate the energy? What if I gave you the energy and I gave you the mass and I said, calculate what the speed of light is, right? So, well, what would you do? You want to get the speed of light by itself. So here you have E equals mc squared, all right? Now, how do you get c by itself? Well, the mass here in the front is a problem, but we know it's multiplied by the mass, so just from solving equations before, we know that we can divide by the mass. We can divide by the mass. And when we divide by the mass, the reason we're doing it is because it's the opposite, and so this mass cancels over here. And on the left-hand side, you're going to have E over m, and that's going to be c equal to c squared. But the problem is, what if I ask you to solve for the speed of light c? Well, let's bring it over here. And we'll flip it around and put c squared on the left. C squared is equal to E over m, right? Like this. Now, in our previous example, we had a very similar equation. It was x squared is equal to 1. Here is c squared is equal to one number divided by another number. Basically, it's a number. Energy divided by mass, whatever, but it's a number over there. How do you get c and solve for c by itself? Well, we have a nasty looking square around it. We're going to undo it with a square root. And we'll undo this with a square root, and we're going to add a plus or minus to the right-hand side. So the square and the square root are going to cancel, and we're going to be left with the speed of light c, which is what I just asked you to solve for. And it's going to be plus or minus the square root of e over m. Now look at that. You've used what I'm basically teaching you here to manipulate one of the most famous equations and solve for the speed of light. So if I wanted to calculate the speed of light, all I would have to do, if I knew how much energy something contained, and I divided by the mass, and then I took the square root, that would give me the speed of light. Now I do have a plus or minus in front, but a negative speed of light doesn't really make sense in our universe. Negative speed, it doesn't really mean anything. So that solution isn't going to matter for that equation. But mathematically, we still put it there because mathematically it's there. But we know that we can't have negative energy, negative mass. We can't have negative time. A negative speed doesn't make sense in this context really either. Or I guess you could think of speed going this way and negative speed going the other way, but that's a little wishy-washy there. Really, there is no negative speed of light. So we throw that away and we say that energy divided by mass, then you take the square root of the thing. That's how you isolate c. So do we really need to do that problem? No. Could you sleep through that? Sure. But it is literally one of the most famous, one of the most important equations in all of humanity, really, that we've ever figured out, and it's within your reach. I want you to know that the things I'm teaching you make things within reach to you. People think some of these things are so far out there I could never understand them, but you can see that you just manipulated Einstein's famous equation, a. All right? So let's rewrite it. A squared is equal to negative 9. All right, so we want to get a by itself, so we're going to put a square root there. We're applying the square root of ourself, so we have to put a plus minus in the front. The radical will cancel with the square, leaving a behind, and you're going to have plus or minus square root of negative 9. Now here we have a problem. I mentioned this when we first talked about square roots. If you don't remember, I'll mention it again. You really cannot take the square root of a negative number and get a real answer. Because think about what a square root means. Something times itself is negative 9. If you put 3 in there, 3 times 3, that gives you positive 9, not negative 9. And if you make it negative 3 times negative 3 also gives you positive 9, which is different than this. So you can't say that but we have to use something called an imaginary number. An imaginary number is not something we're going to talk about today. It's a new kind of number. You learn about new kinds of numbers down the road to solve this equation. But for now, there is no real number on the number line that you know that works here. And the reason is because you cannot take the square root of a negative number and get a real answer. So here's what I want you to say. No real solution. Right? Even though I told you there's actually two answers to this equation, and I'm telling you here there's no real solution, I guess I'm kind of like lying to you a little bit. There is two answers. We are not going to talk about those answers here because we have to learn about something called an imaginary number. But what you will find later on, once you do learn about imaginary numbers, is that there is two solutions to this, two different imaginary numbers to make this thing work. And imaginary numbers has a name that makes it seem useless. It's not useless at all. It's incredibly useful, but they just call it imaginary numbers. So for now, just know that yes, there's really two solutions, but those two solutions are not real. When we say real solutions, we mean the real numbers that we know of, like 1, 2, 3, 4, negative 1, negative 2, negative 3, things like that. Anything on the number line, plus or minus on the number line. There is no number on the number line. Those are called the real numbers on the real number line. None of those work. So if you ever have to take the square root of a negative number, at this point, just say there's no real solution. But in the back of your mind, I want you to know there really is a solution. You will learn later what those solutions are, and they're called imaginary numbers. So for now, just circle that there's no real solution. Anytime you apply a square root and have to take a square root of a negative, that's what you have to write down. Next question. W squared is equal to 4. We want to solve for W, so we have to take the square root of both sides. Why? Because W is squared. We undo it with a square root. And when we do it on this number, so the two solutions that they actually exist for this thing are called imaginary. So they're there, and it's just that there's no real number solution of numbers on the number line. That's why we put this here. but there really is two solutions. We're going to talk about that much later. All right, next problem. Let's take a look at h squared equals 49. So we're going to solve this thing. How? Well, it's not a big surprise. We're going to take a square root of both sides because we want to get h by itself. And when we apply it to the right-hand side, we have to put a plus minus in front. The square is going to cancel with that square root. H will be left behind. Plus or minus will be here. What is the square root of 49? 7 times 7 is 49, so the answer is 7. So this means that h can be positive 7 and h can also be negative 7. This is the answer. Check your work. Put a 7 in here. 7 times 7, 49. Put a negative 7. Negative 7 times negative 7 also is a positive 49. We have two answers. The power on the variable, the highest power, is a 2, so we expect two answers. All right, now let's take a look at something a little different. What about z cubed is equal to 8? Now, this one's different, right? Because it's not a square. It's a cube. But remember, just like a square or a square root can undo a square, what do you think undoes a cube? A cube root. If you have an equation with a power of 4, how do you undo the power of 4? You take a fourth root. If you have an equation with a power of 5, how do you, where I have to take the train off the tracks a little bit, hopefully not confuse you too much. I've been teaching you that for the square root, when you put the square root, you put the plus or minus. When you apply the square root to solve an equation, you put the plus or minus. When you apply the square root to the equation, you put the plus or minus. But when you apply a cube root to an equation, you don't put the plus or minus, okay? And the reason is because when you put the square root, the reason you put the plus or minus is because there's really always equal and opposite answers to the square roots. But for the cube root, it's not the case. Let's continue solving, and you'll see what I'm talking about. Let's figure out what the cube root of 8 actually is. Well, we know that 2 times 4 is 8, and we know that 4 is 2 times 2, and since it's a cube root, we're looking for triplets. So the answer to this is 2. So the cube root cancels with the cube. Z is left behind. The cube root of 8, we just said, is 2 because the triplet of 2's comes out one time. Now, check it. Put the 2 in here, 2 cubed. 2 times 2 times 2. That is equal to 8, so this is correct. So we can check this by checking it and saying 2 times 2 times 2. Well, 2 times 2 is 4, and then the 4 times 2 is 8, so that works. But let's just guess and say, well, what about negative 2? We'll put negative 2 in there. Negative 2, negative 2. Well, negative 2 times negative 2 is actually positive 4, but I still have to multiply by negative 2. And this is negative 8. And this is not equal to what is not equal to the right-hand side. So what I'm trying to tell you here is that 2 is a z is equal to 2. And then you say, well, Jason, you just told me that there's a cube on the z, so it has to have 3 answers, but you only found one answer. Where are the other 2 answers? Well, the other 2 answers are going to be imaginary. And I know I haven't taught you what imaginary numbers are. It's okay. We have to, I said, education is a series of lies. I could have just not mentioned imaginary numbers at all. And I could have just told you that there's only one solution to this, but then I don't want to do that because I want you to know that there really is 3 answers to this. And there really is 2 answers to this. And there's really 2 answers to this, and there's 2 answers to this. But in this case, the 2 answers are not real. And so then I have to tell you, well, what other number can there be besides a real number? It's called an imaginary number. So the bottom line is when you apply a square root to, or a 6th root or an 8th root, any even number power of the root, any even number root, you put the plus minus because of the symmetry of what's going on here. But every odd power, like a cube root, you don't put it because it's, we just showed how the other one is not true. You can't put a plus or minus. I just showed you the negative one does not work out to be true. But in the skills yet, but we will get there, okay? Good. Let's move on. We only have, I think, 2 more. Let's take a look at problem. Looks like this is from a previous lesson. Sorry about that. We'll move along to problem, the next problem here. K squared is equal to 25. Now, this is a square, so we're going to kill that guy with a square root. Right? So, how do we do that? We do the opposite of the squaring operation, which is a square root. When we apply square roots, we always put a plus or minus in front. Here, a minute ago, we applied a cube root. You don't put the plus or minus in front. That's just something we use for square roots and other even roots, like a 4th root or a 6th root. But you don't do that much. It's usually square roots. So this cancels. You're left with k is equal to 27. This is a cube. We know that there's going to be 3 answers, but we suspect that some of them, we might not be able to find some of them now. So let's go ahead and do our work here. How do we get rid of the cube? Well, we have to undo it with a cube root. We put the cube root on both sides. We do not put a plus minus. That's something we only really apply for square roots. The cube cancels with the cube root, leaving behind only c. And what is the cube root of 27? So you can do 27. You know that 9 times 3 is 27. You know that 3 times 3 is 9. You're looking for triplets, as we've done in the past, so the answer to this is 3. And so you get 3. There's no plus or minus here. You don't put that for cube roots. So we say that the answer is 3. We check our work. 3 times 3 times 3 is going to be 9 times 3, which is 27. So we know that it's correct. So we solve this guy. We find one answer based on what we know how to do right now, and that answer is 3. We can check our work because we put it in here. 3 times 3 is 9, and that 9 times another 3 is 27. So it's correct. Where are the other 2 answers? Because we need a total of 3. Those other 2 answers will be imaginary. Actually, more exact. I haven't learned about imaginary and complex numbers. We're going to do that very soon. All right, we only have one more. It's not hard, but it's a little bit more involved than what we have done so far. So let's go and tackle that right over here. And it is the following. Y squared minus 32 is equal to 112. Now here, we do have a power of 2 on the variable. There are no other variables, so we know that there's going to be 2 answers to this. And so we're going to try to get a y by itself. We need to go far away and get rid of the 32 first. So what we're going to say is y squared minus 32 is equal to 112. How are we going to get rid of this 32 here? We're going to do the opposite. We're going to add 32. We're going to add 32 to both sides. So this is going to go to 0. You're going to have y squared is equal to, when you add this together, you get 144. So let's rewrite this. Y squared, 144. How do you get rid of a square on the variable? Well, you do the opposite. You take the square root. When you apply your own square root to solve something, you have to add a plus minus. The square cancels with the square root. You're left with y. And you have the plus minus. And square root of 144 is 12. 12 times 12 is 144. And we have 2 answers. Positive 12. If you put positive 12 here, you're going to get 144. Right? 12 times 12 is 144. Subtracting 32 does give you 112, so that's right. If you put negative 12 in here, times negative 12, you're also going to get a positive 144. And when you subtract this, you're still going to get this. So both values you put in here give you 144, and you subtract this, you'll get the 112. So we know that there's 2 answers here. So take a step back and look at where we started. We basically said, hey, we know how to solve equations, but all the equations we've learned so far have a power of 1 on the variable. And I taught you this general pattern that when you have powers in the variable, it predicts how many solutions you'll have. So a power of 1 on all these equations we've learned so far only have 1 solution. But these equations have a power of 2, so they'll always have 2 solutions. And we showed how applying a square root to both sides, we have to add the plus minus to get the 2 solutions. We've shown how it cancels the exponent to get the variable by itself. We've shown how the 2 solutions we get when we put them in do give us and do satisfy the equation, right? And then we said, hey, let's get some motivation for why we even care about this. One of the most famous equations in all of math and science is right here, and it has a power of 2. And then we said there are lots of other equations with powers of 2, like the area formula for a circle. Area is equal to pi r squared. There's a square on the radius, okay? So there's a power of 2 there. If you wanted to solve for the radius, you have to get it all on the one side and take the square root to get rid of the power of 2 on there. And we actually did that here. We said, hey, we can take equals mc squared, divide both sides by the mass. That'll put c squared by itself. And to solve for c, we'll take the square root and we'll have that plus minus. But in this case, the speed of light, having a negative speed of light isn't really physical. Even though it's mathematically correct, it's not physical. So, but you get the idea. You can manipulate things using square roots in cases where the equation has a square. I just wanted to give you motivation. And then I threw a little bit of a curveball at you and I said, hey, we predict 2 solutions here, but when you actually try to do it, you realize you can't figure out anything when you multiply by itself to give you -9, and that's because you can't take the square root of a negative number and get a real answer. See, some teachers will tell you, oh, you just can't take a square root of a negative. The truth is you can, but you have to use imaginary numbers, which you learn later. So there really is two solutions to this, but none of them are real. So we say no real solutions. And I know that that is probably fuzzy right now, but trust me, we'll learn about something called imaginary numbers. There's two imaginary solutions to this, and so the pattern holds. And then we said, we have situations, well, what happens if we have a cube on the variable? We predict three solutions to this equation, and we do not put a plus or minus for when we apply cube roots of both sides, but we do apply a cube root to get rid of the cube here. The variable gets isolated, we solve the right-hand side, and this is one of the correct answers, but the other two correct answers we can't find now because we haven't learned about imaginary numbers. So in the broader landscape of math, when you solve equations, you can get real answers, real numbers, which are called the numbers on the number line, -5, +2, anything on the number line, negative or positive. Those are all the things that we've learned so far. But soon, you'll learn about other kinds of numbers called imaginary numbers, and they can be solutions also. And I don't want to give too much away and confuse it too much, but just kind of like keep in the back of your mind that there's a broader landscape. There's other kinds of numbers. I know it sounds crazy, but there's other kinds of numbers that we haven't even learned about. And you might say, oh, who cares about imaginary numbers? Trust me, imaginary numbers are incredibly important. It's really not a great name. They should be called something else because they're very, 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 very important for all modern theories and subjects. So I'd like you to solve these. The main takeaway, to undo a square, you apply a square root. When you do that, you have to put a plus or minus to get all the answers. When you undo a cube on the variable, you apply a cube root. And you're not going to get all the solutions, but you'll get at least one of them, and you do not put that plus or minus in that case. We showed why here. Solve all of these, and then please follow me on to part 2. We'll get a little more practice with using radicals to solve equations.